Another really interesting way that you can modify lesion depth and create larger or smaller lesions is by adjusting where you place the indifferent electrode on the patient's body, or whether or not you put one or two of these electrodes on the patient's body. So let's spend a moment to understand why that is the case, because it can really affect lesion size. Your RF generator, usually the number that we're playing around with on the RF generator is the power or wattage number. So this number here is 27 watts, and we might dial it to 30 watts or 50 watts, something like that. And when we're dialing power on the generator, power can be thought of as the pushing force for current flow. So if power is the pushing force of current flow, dialing 50 watts, or in some cases up to 90 watts of power, results in a strong pushing force of current. And so the generator will very strongly push current through the wires connected to the generator, to the catheter, through the wires in the catheter, out from the catheter electrode tip, and then through the tissue, and then collected by the indifferent electrode, and then back to the generator again. So this is your circuit. So current is constantly flowing like this. And if current is constantly flowing like this, what you're dialing when you're dialing up the power or down the power is you're dialing how much is the generator pushing this current. So if you dial 50 watts, then you're pushing quite strongly. If you're dialing 15 watts, 1.5, then you're pushing current quite weakly, and only a bit of current will flow. So that's what you're changing when you're changing power. You're changing how strongly is current pushed out of the RF generator. That's one way to think about it. I'm trying to keep this as least mathematical as possible and more conceptual. So that's power. But this electrical circuit also has an inherent resistance. So the materials in this circuit aren't superconductors of electricity, right? We have wires that are fairly low resistance to current flow, but then we have blood pool, and we have cardiac tissue, and we have other tissues in the body, and these tissues aren't incredible conductors of electricity. And so there's a certain resistance to current flow that happens. And what that means is that if you have a high resistance circuit, so let's say you have a high resistance circuit, that means that there's less current flow. And current flow is usually indicated by the symbol I. Don't ask me why, I'm not sure. So if you have high resistance, but you have a low power, low pushing force, then there's a lot of resistance resisting current flow, acting as a barrier to current flow. And if you have a low power setting, so let's say you have, 10 watts, for example, then you have very weak pushing force to overcome that resistance, which means by the time the current gets to here, there's very little current being delivered to tissue. This is an incredibly important concept to understand, and we're going to go through in the next slide how this directly relates to lesion depth. So let's imagine that we have our patient here. This is our expertly drawn patient. This isn't our usual artist. This is my drawing. And this patient has a heart rather centrally located, and then we've got an ablation catheter coming up from the groin, and we're ablating the ventricle. We've dialed 27 watts, and so that generator delivers current to the catheter. Then that current goes up through the catheter, and it comes out of the ablation electrode to create a lesion, causing resistive and conductive heating. Then that current has to go through the tissue to be collected by the indifferent electrode and then back to the generator again. So we have a certain circuit here. And this part in particular, this tissue part, accounts for a lot of the resistance of that circuit, because tissue is not a great conductor of electricity compared to the copper wires or the metal wires that are located inside these catheters and cables. So let's say our circuit resistance or our impedance, right, let me get rid of that. That was really bad drawing. Our impedance is, let's say, 100 ohms. And we've dialed a certain power. And let's say we've dialed 50 watts. So we've dialed 50 watts of power. And the current delivery in this case, if you work out the equation, so the equation is power is equal to, I'm not going to get very mathematical here, I just want to illustrate a point. You don't need to remember this, but this is the power equation. And so what this means is that the current flow, so hang on, this is power. So we've got a resistance of 100 ohms, and we've dialed 50 watts on the generator. So let me put 50 here. So that means our current flow is about 0.7 amps. So current delivery is equal to 0.7 amps. And remember, it's current delivery that directly affects lesion size. The more current we deliver to tissue, the more heating we get, and the more lesion we get. So we're delivering a certain current here with our circuit, and that current is sufficient to cause transmural efficacious lesions. We're really happy with our lesion depth. We're getting full transmurality. For whatever reason, we want to maximize lesion depth in this procedure, and so we're maximizing lesion depth with this current arrangement. So everybody is happy. Then, for whatever reason, the blue electrode stops working. Maybe someone tripped over the cord that connects to the generator, and that broke the cord here. So now this is not working. So now there's no circuit present, so we can't deliver energy because this part of the circuit is broken. So we can't continually have this kind of circuit happen. So we need to replace the indifferent electrode. Okay, so let's replace the indifferent electrode. It's hard to get to the patient's back during general anesthesia, so the cardiac physiologist places the indifferent electrode on the patient's calf muscle because it's more readily accessible. It's also close to the RF generator. So okay, we've placed it on the calf muscle. Now we can deliver current. That current goes to the catheter, and then that current goes through the body all this way to the indifferent electrode and then back to the generator again. So now we have a current forming again. So we go to the catheter, through the tissue, to the indifferent electrode, back to the generator again. And this continues on. So we've got a circuit, we can deliver energy. But what you'll notice is that the current has to go through so much more tissue in order to complete the circuit. The circuit is much larger, and the circuit, the electrons, have to travel through a lot of tissue now to get to the indifferent electrode. So now the circuit impedance has gone up by a lot. So it might be 180 ohms, for example, now. Now previously, we were happy with our 50 watt lesion size. But what that means is resistance to current flow is a lot more. There's a lot more resistance happening to current flow here. Because there's a lot more resistance happening, that means that less current is actually delivered. So instead of 0.7 milliamps of 0.7 amps, of current, we're actually delivering somewhere around 0.5 amps, which is about a 30% reduction in current delivery. So we're delivering 30% less current. We still have the same power settings, 50 watts. The only thing that has changed, we have the same generator, we have the same ablation catheter. The only thing that has changed is the location of the indifferent electrode. And that means that resistance is now higher, and so current delivery is lower. Lower current delivery results in less heating and less lesion formation. So now our lesions may not be transmural, or they may not be as efficacious, even though we're using the same settings on the ablation generator. This is how much of a difference the location of your indifferent electrode can make. In general, placing the indifferent electrode or the return electrode closer to the heart results in a lower baseline impedance because there's less tissue between the heart and the return electrode, and therefore more current delivery, and therefore more heating, and therefore greater lesion size. Placing the return electrode far away from the heart increases circuit resistance, impeding current flow and impeding lesion formation. Not only can you alter where you place your indifferent electrode, but you can also place a second indifferent electrode on the patient. Placing a second indifferent electrode on the patient increases the surface area where current is collected, which means there's less inherent resistance to current flow. Less inherent resistance to current flow lowers baseline impedance, which allows for greater current delivery to tissue for the same power settings, and therefore greater lesion size and depth. So putting two indifferent electrodes on can help promote improved current flow and therefore greater lesion depth, and putting less indifferent electrodes on or cutting them in half so that they're smaller increases impedance to current flow and therefore reduces lesion heating and depth. I would encourage you to read this paper, even just the introduction. It explains this concept really well, perhaps better than even I can explain it. But this is a visual diagram of how baseline impedance can affect lesion formation. Here you can see a much larger lesion as a result of a lower baseline impedance for the same power setting compared to this lesion, which is much smaller. Both of these lesions were performed using the same ablation catheter and the same duration of ablation and the same power settings on the generator. The only difference was the baseline impedance. So this lesion could have been created by placing two indifferent electrodes on the patient, perhaps on the right and left scapula, pretty close to the heart, and that results in a lower overall impedance from the ablation catheter to the generator. And these go to the generator and then back to the ablation catheter. Whereas this one here, this is a much smaller lesion. So maybe this is the kind of lesion that you get when you place the indifferent electrode on the patient's calf muscle far from the heart, where it has to go a much larger circuit and therefore higher resistance to current flow. So placing the indifferent electrode close to the heart helps to minimize the amount of current resistance, which means that when you dial 50 watts on your ablation generator, you maximize current delivery to tissue. Maximizing current delivery to tissue maximizes lesion size. So for the visual learners, this is the kind of impact that this can make. This is a model where An ablation catheter was ablating for 30 watts for 20 seconds and 10 grams of contact force for every single lesion. So theoretically, we're pumping the same energy into the tissue. However, this lesion occurred during a baseline impedance of 224 ohms. So for example, you put the return patch on the calf muscle, one return patch on the calf muscle, and you got a lesion dimension of this. Compared to this one, where a baseline impedance was 106 ohms, so this is kind of analogous to putting two indifferent electrodes on the back, for example, right scapula, left scapula, something like that, and delivering the same watts and for the same duration on your ablation generator, but the lesion dimension is double the size of this lesion dimension. So this can have a huge impact on your lesion size. So some physicians will really preferentially want to double patch or put two indifferent electrodes on. Other physicians will be happy with one, but they'll be picky about where that return electrode is placed, for example. And you can try this. You can put two patches on, or you can experiment with putting a patch in different locations, as long as your physician and everyone is aware that you are doing that. And you'll see that the baseline impedance does change depending on where you put the patch in relation to the heart, or whether you put one patch on or two patches on.